Many previous work had been done for the avoidance of obstacle, and most of them try to do something to track the predefined reference with fixed obstacle. This method is quite fragile for the sudden appearance of obstacle. So in our project, we try to design a local dynamic obstacle avoidance MPC. This design for MPC has three features, including the obstacle detection, avoidance path generation, and path following, respectively. So in our scenario, the vehicle is running along the predefined straight line, and when the sudden obstacle appears, our vehicle will try to detect it and turn left or right to avoid the obstacle with steering angles as small as possible. But however, as we have seen, the constraint for the obstacle is not convex. So efficient method based on the sequential convex programming is applied in our implementation. The first step of our project is try to use a simplified kinematic bicycle model to simulate our systems. So there are four states. There are coordinates of vehicle x and y, velocity v, and the angle of current velocity with respect to the longitudinal axis of the car, which is called phi. And for the inputs, there are two inputs. One is the acceleration, and another one is the steering angles. They are called A and C separately. So during our simulation, the model is discretized with a sampling time 0.2 second, and for the MPC part, when we do the MPC for the leading car, only the steering angle is considered because we try to simplify our system and decrease our computational time. And for the following parts, both the steering angles and acceleration will be considered as our input.
Hi, I'm Jason. I'm going to introduce you about the algorithms and the results of the MPC obstacle avoidance of the leading car. In this case, we apply sequential convex programming and the interior point solver to iteratively solve the real-time path planning and tracking. The prediction horizon we have is 5 time steps. Each time step is about 0.2 seconds, which is also the sampling time in our system model. In the beginning, the obstacle is not found, so the obstacle constraint is not considered in the optimization. And when the obstacle is found in the prediction horizon, since the obstacle constraint is non-convex, we actually form a convexified constraint by linearization. The linearization takes in operation point the x and y coordinates of the previous step in the iteration. And then we use sequential convex programming to iteratively solve the optimization with slack variable. The slack variable is self-constrained, helps the iteration violates the constraints before the iteration finally converge to a certain value. As you can see, in our simulation, we have 4 obstacles. Each have a 1 or 1.5 meters in radius, and also 2 meters of safety region surrounding the obstacles. We have the parameters shown in the PowerPoint. We want to have the penalty on Y lower than the penalty on X. That's because we want to have the truck not coming back to the original track too quickly after avoiding an obstacle and soon encounter another one. The rho and epsilon is to have the sequential convex program iteration converge properly. The derivative steering angle is limited to avoid oscillation, which occasionally happens when truck encounters an obstacle which center is just on the original track. The prediction horizon n is actually a key parameter in your design. If the n is too large, the computation time is too high. If the 2m is too small, the truck's reaction to the obstacle is too late and would cause the truck unable to avoid the obstacle clearly. When the n has the value about 5, 8, and 11, then the average computation time are about 1.5 seconds, 4.2 seconds, and 9.3 seconds. So clearly the computation time is a huge problem here, and some improvements should be made in the future work. So in the future, which is also we're trying now, is the semi-definite programming relaxation, and also we want to directly implement the solver rather than through the AMIP. We were trying to do both of things, but due to constraints, we will keep doing that in the future.
Okay, let's talk about the following portion of our project. Nowadays, autonomous cars are becoming more and more meaningful. Automating and managing a fleet for the purpose of cargo transportation or mass transportation is becoming a very popular topic and worth studying. As we notice that avoiding both static obstacles as well as dynamic obstacles, in this case, the car's preceding leading car is quite difficult and challenging. So we did the dynamic path planning for the following car by taking the leading car's historical positions as references, which simplifies this issue. And we can use model predictive control methodology to tackle this issue. Okay, let's move on to the second page. So this page shows the general structure of the following part. It consists of 3 main portions. The first part is taking the leading car's states planned, manipulate the data. The second part is the main body, which is an MPC reference tracking controller, where car B taking the leading car's position as reference, adding some dynamic safety buffer distance on top of that, minimizing the performance index, iteratively following MPC methodology, and eventually passing the data to its follower car C. Same as car B, car C would accomplish the following task. The last part is the output of the MPC planning, which gives the instructions for car B and car C, the acceleration and the steering angle to forward past the scenario. There are some notes we have to concern about. The tracking reference for the following cars are modified by concerning the following 2 factors. The first is obstacle avoidance requirements, so we need a safety buffer. Another one is anti-pileup requirements, which require us for a time delay, and also another dynamic safety buffer. So in this page, we can see the result for the MPC path planning of the following cars. The figure on the left shows the speeds for follow car B and car C with respect to the time step. As we can see, their speed profiles are pretty similar, which are what we should expect. The figure on the right shows the heading angles for follower car B and car C with respect to time, and their shapes are also quite similar and consistent. During the simulation for the car following sessions, there are some critical parameters influencing the performance. Firstly, a longer MPC horizon length gives a better performance, but it definitely costs longer computation time. The ratio of Q to R determines the relative penalty weights on the tracking accuracy and input modestness. In another word, for more precise path trajectory, the input modestness has to be compromised. Another factor is the reference delay time, which depends on the dimension of the car model. For bigger cars such as a truck, the delay time should be longer to maintain a reasonable gap between adjacent cars. So in conclusion, the following portion of our project is quite successful. It can follow the leading car's positions quite accurately with a relatively modest input control.
Finally, we built a 3D visualization application based on WebGL to research the results of MPC simulation. A truck 3D model was introduced in this application. Several obstacles were introduced in the application as red circles. The green circles around the obstacles means safety area. The application used data from state variables, input variables, and output variables of MPC system to drive the WebGL animation loop to visualize the real-time positions, velocities, steering angle, heading angles, and so on. The application also set the parameters of the WebGL camera to follow the car in real time. This is the 3D animation application of this project. On the left side, we can watch the heading angle and the steering angle of the first truck. On the right side, we can observe the relationship between these three trucks and that between trucks and obstacles. With the visualization of the MPC results, we can easily watch all of the parameters in real time and then check the algorithm. We can also get feedback of our control system design to improve the efficiency of the system. For more detail, please visit www.oparp.com/car.